Sreejith sir, may I begin with instructions and all of you to keep the mic and camera off during the session, during the complete session. And do not share your screens during the session. And your doubts shall be typed at any point in the chat box along with your name and class, which we will collect and shall be read out during the Q&A session. And regarding the language of the question, it can be in English or Malayalam both. And it's already 3-2, so I think we can begin the session with the introduction. Good afternoon to all. With utmost warmth and respect, I extend a cordial welcome to our revered mentors, esteemed scientists, distinguished academicians, inquisitive students, and all the passionate participants gracing this occasion. Today, we gather here for a momentous milestone, the 75th session of the UL Space Club's webinar series, a tradition that continues to illuminate minds and inspire generations. UL Space Club, operating under the aegis of ULCCS, stands as a beacon of knowledge, dissemination, and collaboration. ULCCS, Asia's largest and the world's second largest labor cooperative, owes UL Space Club's unparalleled legacy to the visionary leadership of Sri Ike Kutisa, former director of ISRO. It was his foresight and dedication that sowed the seeds of this club, which has now become a crucible of innovation and dialogue. The webinar series began its humble journey in May 2020 during the initial waves of the pandemic, as many of here remember. Over the years, almost 5 years it has transformed into a celebrated platform uniting veterans from ISRO, VSSC, IASC, MIT, IITs, ISRs, NITs, and numerous other prestigious institutions and startups, both national and international. The UL Space Club extends beyond the webinars, sparking curiosity through the Sky Safari group, the Astronomy group, R&D projects, paper presentations, Stellar Chronicle magazine, space camps, Stellar Media, and other exciting events. As a registered space tutor of ISRO, it bridges young minds with the cosmos. This occasion would be incomplete without acknowledging the pillars behind this initiative. My heartfelt gratitude goes to Sri K. Kuti sir, Sri K. Jairam sir, and most significantly, Sri Sreejith sir, the unwavering moderator of every single session. To my fellow team members and our dynamic student lead, Varun K., and you all have been the lifeblood of this endeavor, this journey. Together, we have not merely organized webinars, but have created a thriving community, a family, webinar family that bridges the gap between science and society. Today also marks a symbolic milestone if we include the special sessions conducted to commemorate Moon Day, Kalam Memorial Day, Space Week, and other momentous occasions. This is effectively our 100th webinar. I'm not exaggerating. As we now in a new year filled with opportunities, let us celebrate the success of missions like SpaceX and take pride in the contributions of our members such as Sayuj, Varun, and Danish, who have worked tirelessly with renowned organizations like Anand Technologies Limited also. Yesterday, I came across an inspiring reflection from our Honorable Prime Minister. If you would have watched that or heard that, Sri Narendra Modi, during his first podcast, emphasized how space achievements like Chandrayaan have ignited a spark among today's youth. He said, children of grades 8th and 9th are now closely following Gaganyaan's timeline, the training of astronauts, and even the intricate details of the mission. Such is the strength of social media and communication today. As part of this great enabling force, UL Space Club continues to empower young minds and fuel their curiosity, standing tall as a torchbearer of this intellectual renaissance. On this very special day, we are privileged to have with us Dr. Sreejith KJ, an eminent scientist from VSSC and the head of the Ceramic Matrix Compositors section. Today, he will take us on an enthralling journey through the story of elements, a topic that connects the intricacies of chemistry with the vastness of space. Telling a story demands passion, enthusiasm, and deep knowledge, and we couldn't have for a more capable guide for this exploration in chemistry. With great respect, I welcome you, sir, to our platform. Along with that, I welcome every single person present here in this virtual platform to our webinar. Without any further ado, I now hand over this session to our mentor and moderator, Sreejith sir, to introduce our esteemed speaker. Thank you.
Thank you, Sriram. We are so proud to hear from you, our legacy and our previous activities of UL Space Club. And we ever thank to our mentor and founder, UL Space Club, E.K. Kutisa, former director ISRO. And we are sitting on the 75th session. So it's a great wonder for us. And when we started the time of pandemic, when the people are not connected, and still we could continue that with excellence and excellent support from various institutes, ISRO and other research institutes all over the world. And today the topic is the chemistry and space, and it's a very interesting topic. And we know the chemistry is everywhere. Our life is there, our existence is there, our constitution is there, and that's happening in the universe. That's the all answers for this universe and all the activities that's there. Here is the answer is from chemistry, and it's the application part. Today we get an eminent scientist from Vikram Sarabhai Space Center, Tumba, and we are getting support from that great institute, the part of ISRO, for the past few years with great speakers and these things. And today the topic is so interesting, and we are directly connecting these things to the very fundamental aspect of science, that's chemistry. And we proudly presenting Dr. Sreejith KJ, and I am so happy to read his profile here by inviting him. Dr. Sreejith KJ is a material scientist with expertise in polymer-derived ceramic materials for space applications. He started his research life at Vikram Sarabhai Space Center, Thiruvananthapuram, as an ISRO Research Fellow in 2004. His PhD research, guided by Dr. S. Pakirisamy, was on the synthesis of novel pre-ceramic polymers and ceramic conversion of mechanisms. During his postdoctoral research with Professor Rishi Raj, University of Colorado, USA, he had carried out studies on polymer-derived ceramic materials for energy storage applications. He has worked as a research associate with Professor Peter Greel in the Department of Material Science and Engineering, Glass and Ceramics at the University of Erlangen, Nuremberg, Germany. At Erlangen, his work was on the development of polymer-derived cellular ceramic structures. Currently, he is the head of Ceramic Matrix Composite section in the Ceramic Matrix Products Division of Vikram Sarabhai Space Center, VSSC. And at VSSC, he has developed a pre-ceramic resin of fabrication of wing leading edges of reusable launch vehicle and ceramic matrix composites via chemical vapor infiltration for hypersonic engine thermal protection systems. And his material of interest in carbides, oxycarbides, max spaces, and carbon materials. And his research guidance in PhD 1 student, MTech and MSc students, and his publications in the international journals, and 17 publications are there. We are proud to invite these great scientists of India and the future of ISRO. We could say that the background is for the development of new spacecrafts and all these things, development of materials. And with his hands, the ISRO can rise to the realm of 21st century's leading space exploration organization in the world. We expect more from these young scientists, and we are proudly inviting this to forum of UL Space Club. Along with that, I invite Dr. Sreejith Chandran. He is continuously supporting here, sir. You are also inviting, welcoming this forum, and we have Jairam sir and all other veteran scientists of ISRO, and the students are the most important target of our program. They are curiously watching and asking questions. We will have the presentation, and after that the students will flourish this session with their questions. And without taking much more time, I invite Dr. Sreejith to present this interesting topic of chemistry and space in this forum. Welcome, sir.
Thank you, sir. Thank you. So shall I start, sir?
Yes, sir, please.
Okay. To start with, I'll just switch on my camera for a while. So, good afternoon, everybody. Actually, I'm so much humbled to be part of this great endeavor, great mission started by Ike Kuti sir to ignite young minds. And through these speeches that he is organizing, or the club is organizing, I'm very happy to note that people are getting interacted with the people who are actually working on space science and technology. So I'm humbled by the introduction, remarks and all. And also by the fact that this is the 75th in the series of speeches. So I will try my level best to live up to the expectations. So my dear students and the mentors, the respected mentors, and I also understand that my seniors from VSSC is also joining. Sreejith sir, Harikrishnan sir, there's all my mentors. They're always been there for supporting us for interacting with the people and tell what we are actually doing in very plain and common language so that people can understand. So that kind of endeavors or that kind of activities, particularly Sreejith sir and Harikrishnan sir, they are basically most interested in, and I am here as part of that also. So with a small introduction, I will now start my presentation. I will switch off the camera for a while, maybe the bandwidth issue. I will switch it on after some time. I think it's okay. I hope the screen is visible right now. Sreejith sir? Okay, 1 minute. Right now? Okay. Okay. Thank you for the arrangements, and thank you for the introduction also, sir. So I will start now. Basically, when this particular topic has come, I was in dual minds, in the sense that usually when we present our scientific data, there are two types of presentations, as you know, maybe. There's one is inside the VSSC for tough reviews. The second one is for scientific seminars and all. These two actually we are always okay with that because we have been doing that for quite a while. But when we have to prepare or we have to interact with the young minds of this country particularly, and as the introductory, I think Sreeraj has told, as Prime Minister has told, people are closely watching what is happening in ISRO particularly. So in that aspect, I was thinking how to make a presentation, in which way. Then finally, I have thought that, okay, people like stories. So let me prepare, a story based on the role of chemistry in our space endeavors. So the core of the presentation is in the materials that we are right now developing, or in the future what we are going to develop in that sense, particularly the area that I am working right now. And but then I thought I should have a beautiful introduction into that chemistry part. Then thinking on that, I found that the formation of elements, how all these elements have formed. That most of the people are in high school, so you must have seen anyway the periodic table. You have been accustomed with the use and reactions of all these elements, and we have studied that basically, But then how did all these things started? All the matter came into being, The chemistry comes into play once the materials are there. When the energy is there, the physics people can talk more on that. When the matter is there, when the matter is created first time in the universe, after that only the role of chemistry starts. So I have just added one introduction onto that part, then our core area on the materials, then in future, in which direction actually are we going, or we are supposed to go, just to so that you people can be better prepared to take up that challenges. So in that way, I have a prepared. So let me start by showing the photograph of an eminent personality in this regard. Hope most of you are familiar with this photograph. Just giving a moment to think. This is Dr. Prafulla Chandra Ray, regarded as a father of modern Indian chemistry. He has lived in the pre-independent era, had a good educational chemistry, then has made the first research lab, the full-fledged research lab in India. Was a main reason for starting a lot of industries in India. And basically, in the chemistry point of view, he has done some wonders also, in the sense that he has made compounds out of a lot of inert materials, in the sense of nitrates of mercury, for example. So he is regarded as the father of modern chemistry. And as we know, before we start anything, we put pranams to our gurus. So personally, myself also, why I'm sitting here is because of the number of teachers from the school days to my college days who has guided me and still guiding me, and those who have made me what I am right now today. So with that pranams, I start my presentation today. And as I told, we have 3 chapters. So I just divided the presentation to 3 chapters. Sreejith sir, I'm audible clearly, no?
Yes, sir, you're clearly audible.
Okay, I just think because this kind of an interaction, I'll not get the feedback. So
Yes.
excuse me, I'll be asking between for some sound feedback.
Sure, sir, sure.
Okay. So yeah, I'll continue there. So as I told, you have 3 chapters, and in the first chapter, I would like to start by telling you how all these things have begun. The second chapter is about the materials now. No, I'm not going to, bore you with the full list of materials or something, but I just trying to tell you how we are making it, how we are doing it in ISRO. How if somebody is coming up to you and telling, I want this, a particular type of material with these properties for this use, how you start the whole business, how you do it in that way. And the chapter 3 is for the future. Okay, this for you people. Mostly the responsibility lies with you for that. So some guidelines for that, or even some pictures for that. So we'll start with the chapter 1. So let's start with the chapter 1, the beginning, the birth of elements. As we know, there are a lot of theories about how the universe come into existence. And you must have heard of a lot of lectures of eminent speakers speaking about that in YouTube videos or in the Space Club itself. I'm not an expert on that, but my interest lies in the fact that the matter, how the matter came into being was my question. Because when we started everything, we know that everything started with a Big Bang. That means there was an atomic what you can say, a form of the whole universe. The whole universe was actually contained in a small point, so dense, so hot. And at a particular point, it exploded, or in the sense that there is a big bang. And starting from that particular point, the universe was ever expanding as it is right now. And along with that, the universe is cooling also. So these 2 things you keep in mind. The universe is expanding and it's cooling. Excuse me?
Spacer?
Yep. Okay. So what I was telling was that initially there was no matter to start with. There was Big Bang, and at that particular micro, or 10 raised to minus 9, 1 by 1 divided by 10 raised to minus 9, 10 raised to 9, that kind of a fraction of a second also, the matter was not existing. So the Big Bang, the facts, you'll get better idea. Maybe you are having better idea. To start with, we know that it is 13.75 billion years ago, and the 1 billion is that much zeros. So it is so quite, early. And the idea that you have to carry in your mind was that there was a hot and dense point in space. And after that, it starts expanding and started cooling. And during this cooling and expansion, what magic has happened is what, as a material scientist, as a chemist, I'll be much more interested in. This is a particular photograph, or not, it's a a drawing made based on scientific facts. If you could understand what is it is, just keep it in your mind. I'll ask later. But this is the picture of a proton. So when I started my, when I was doing my school in Trivandrum, in a government school, Nedumangad government school, we are taught that, or after some time also it was taught that the fundamental particles are protons, neutrons, and electrons. So during this time frame, the story has changed, as you may be aware also. Proton is no longer a fundamental particle. Neutron is no longer a fundamental particle. It is made up of finer fundamental particles called quarks and gluons. What you see, the red particles are quarks. They are up and down quarks, and based on the color it changes. They're held together by another kind of material. It's called fundamental material called gluons. Anyway, this is a particular structure of a proton, and these kind of elementary particles it was there just after the Big Bang, and they started when it starts to cooling. When the universe starts cooling, these kind of started accumulating together to forms that we know. We name it as protons, neutrons, and electrons. As we know, inside the proton and neutron, the basic things are quarks. And the basic requirement for this to happen was the cooling of the universe, because you need to put all these simple quarks and things back into a structured space. You have to give out a lot of energy for that. So the main thing is that if it is too hot and if it is bringing with a lot of energy, that cannot happen, and it has to cool down. So the universe would have sufficiently cooled down so that the energy can be converted into matter. So the energy was converted into matter because the universe has cooled down. That's one part. And during that particular thing, the universe was filled with all these fundamental particles as dust, what we call as a cloudy phase or something like that. Nothing was there. And inside that cloud, as you know, mostly these protons and neutrons starts combining and forming deuterium, tritium, and helium kind of material. So that was the thing. So there was a cloud made up of all these guys there, and the universe was cooling down. And here, one thing you have to keep in mind was that when I discussed with you that the element was formed, this element was formed, you don't think that the atom or the complete atom was formed. What I was mentioning is about the nucleus only, because for an electron to come in an orbit around a nucleus, still a lot of energy has to be given away for that stabilization part. So for that amount of the atmosphere atmosphere is not the right word. The universe should be cooled down still further. So the atoms will be forming George must have taken thousands of years. What we are right now discussing about the nucleus is only. If you look at the nucleus of hydrogen, it contains only one proton, as we are studying in our school classes. And these protons, deuteriums, tritiums, and everything were there. And what we required at that point was a little bit heating. The whole thing was cooling down. And we need some, like we are standing outside in a winter day, we are looking for some hot spots, to be around. So that thing happened in the cosmic consciousness, we'd call, how it happened. It's that is beyond my my understanding, but I know that it happened. So what happened is that this hydrogen nuclei, basically the protons, starts fusing together, what we call the fission, and then the first self-sustaining nuclear reaction starts forming. Oh, this was the fundamental, turn we have taken, in the sense that otherwise there's a cloud that exists and the universe was cooling down, nothing happens, it goes on well. But at that particular moment when the self-sustaining nuclear reactions began, and the dust and cloud started feeling that, okay, we exist as matter. That consciousness we call gravity sometimes. So this particular matter starts forming, matter, no, I exist. They start to, form dense clouds. Inside that, the fission starts. There's as we ignite something, or we are starting the star. the star is being born. So a star is being born in the, in the clouds of all these fundamental particles. And at that point, the universe was cooling down, but at the same time, we have now a source of generating heat or generating energy by nuclear fission, nuclear fusion. So then comes the next guy. The next guy in the line is helium. We know from the, the periodic table, we know the next guy is helium. And helium nucleus starts forming by the combination of, 2 protons and 2 neutrons. So the equivalence of 4 hydrogen atoms should involve there. So they just fuse and they form helium. So that was the self-sustaining reaction that was happening inside the core of the stars. And but this reaction also releases some form of energy. This is not new to us, no? This way that I am talking, we are very clear that this is what is happening in our sun. The fusion of hydrogen to helium. So this has been happening for, that number of years that we cannot count with your fingers. Or so that many hydrogen conversion to helium is happening, and in sun also that's a major form of energy release. But what is happening is that this energy further. One more point I just want to show you. Yeah, this was interesting because helium starts forming. The same helium that was formed in the heart of a star for the first time after hydrogen, the second member in the family. That is still the same helium that Morgan Freeman is inhaling in this video. You just see that. And what is happening in them?
There we go. You ever want to go to space? I really shouldn't be doing this.
Okay, sorry. Just gone back. So what I was telling was that this, we know all these funny moments when we inhale helium and we try to speak. And the reasons you'll find in Google, you'll find it. But the basic thing is, and the type of resonance that is happening, the speed of sound inside the helium is high, and it should increase to some high frequency, pitch some high frequency. It will select some high frequency sound waves specifically, compared to the resonance with our vocal cords. Anyway, helium is a wonderful material, and the same helium. It's not all fun. Helium, though, basically we see that it's for for its color, for this funny use being used. Helium is also used for treating lot of diseases with respect to your voice track and everything. So, and helium is also used as a very good efficient cooling liquid for cooling machines and for storing cryo materials and all. So helium is a very good in that way. Though it is very simple, it has very good applications in that, and we know how helium is formed now. It has formed along with the birth of stars. So helium is formed along with. So these two are parallel and almost in the same time it happened. If you take the attendance of the big periodic table, we have only 2 members at this time, and the star is just born. It's a newborn baby. Now what happens is the star starts growing. How it is growing? Simply because these type of fusion reactions, what is happening inside the stars keep on increasing. It increases the heat, and when the heat has come to a particular level, which is enough for the formation of higher nuclei, simply that happens. So when the star grows, there are some elements forming or growing because of the high heat that the star is producing at that point. The 2 heliums can combine together to form the beryllium, carbon, oxygen, neon, and up to magnesium. You will see that red giants up to magnesium you can find. Our sun will one day become red giant. That's the story, and what we are afraid of also. Anyway, up to magnesium the story goes well, and you can find that the big guys have come here already. The carbon, the main source of our plant life, or even the our animal life, including us, the oxygen and the magnesium, all these basic elements have already formed during the growth of a star, and we have come up to magnesium right now. And for furthering this particular thing, and all these things happened by addition of helium. So helium was a basic building block, not hydrogen or proton. You keep in mind that. So the helium was a basic was getting added into that. And for the formation of the bigger guys, like starting from magnesium to nickel, we need a little bit more temperature. The temperature has to be increased. If it is in a stove, if it in a normal cook range or something, we'll still increase the flames. In that way, what happened to the star is that the energy already being released during all these reactions has increased steadily, and the temperature has reached to a still higher level. And then at that particular level, not the helium formation addition, but another thing happened, which is called the exchange of protons and neutrons. So whenever there is a high amount of freely available energy around, all this matter loves to be exist as fundamental particles, not as compounds or something. In another way, in a normal world, we call it a decomposition. But in a high energy states, all these guys actually, are present as in their fundamental, but they love to be like that. And under higher temperature, that kind of reactions will also happen. So because of this proton and neutron exchange reactions, the addition happened to the nucleus still further. And then we have come up to nickel. Oh, that was a wonderful feat, because nickel is the most stable nuclei ever known. It's not one of the most stable element or something, because element, when we call the chemical reaction stability comes, electrons comes, so that is in a later stage. But with respect to the nuclear stability, which is actually a ratio of neutrons to protons and all, we must have studied that, the N by P ratio. So nickel has formed, and during the time, the star has also become something called a bigger, it has reached its maximum size, it has reached its prime of its life, and we call such stars red supergiant. So if you look at a red supergiant, you will see a core of iron and nickel. Why I call it core of iron? Because they are high dense materials. It should sink into the core, and it has gravity. So big gravity is there. It will sink into the core. So anyway, in red giant, we have reached up to nickel. We are good attendance there. Now it's the other part of the story. With all the energy what is getting produced during these reactions, the fission reactions in a red giant, it's not enough for the formation of the further nuclei. The still higher elements, members are there. That happens by an entirely different process. That happens not by the addition, like, if you keep on adding from nickel, the story stops there with nickel. Now what happens is that we need a little bit more energy. And with that energy, every other element, the higher elements, higher weight elements has to form from the fundamental particles again. So it is a different mechanism. So what the fundamental particle, what we call as neutrons, there are variants, based on the quark numbers and its colors and all. But basically the neutrons, what we call, these neutrons has to be plenty available with a lot of energy, lot of temperature there. Then only the remaining elements can form. The story goes like that, but you don't never think that this universe has formed for the creation of all these things like we do a chemical reaction. But this was going, this was both happening at the same time. This was the way that universe was evolving by the creation of new elements. That was an eventuality, like that was inevitable. The formation of heavier elements are inevitable in the growth and death of a star, or even the universe as we call. The star is going to die. When the star is dying, actually it is like a balloon. It expands to some point and then it explodes. What is actually happening inside is that there is a competition between two energies. The gravity of the heavy elements being formed is actually pushing the star to the core. But at the same time, the amount of energy being released by the fission reactions are actually asking them to expand. But when this fuel runs out, like in when the vehicle fuel runs out, which comes to a stop, the fuel of hydrogen and helium fusion reactions, hydrogen and helium fusion reactions come to a stop. Its fuel is over, so the outward push is over. Now the whole gravity comes into play, and it shrinks in a fraction of a second. It shrinks back the star to a star. It shrinks a star. All these things. Supernova, what we call the explosion, happens just after that. Because of the shrinkage, some more energy is created, and that causes the explosion. But what remains are two things to keep in mind. One is a core, which is left behind of a earlier star, which is filled not with iron, not with any other element, nickel or something, only neutrons. So the neutrons actually is a very dark object. It's so dense that atoms no longer exist. It is actually, we know now, that is as dense as the nucleus. The whole weight of the atom is in the nucleus that we know. It is the densest area in the universe is the nucleus of any atom. So the whole neutron star is in that condition, that much highly dense. So inside that, it is in a mayhem, like whatever can happen. You put a lot of small children in a room and close it, the way that the mayhem they'll be creating. In that way, it's a free playtime for the neutrons. They capture, they grow into bigger nuclei, and all the heavier elements will form after that. So these elements, the elements after nickel, are basically formed during the death phase of a star to a neutron star. Other things have formed in the earlier phases, and different mechanisms. So this is in a nutshell. The star grows into a red giant and it dies by a supernova. But the death is actually seen in a philosophical point here. A star never dies completely. It's not the end of a star. Whenever the supernova happens, all this dust which is actually thrown out into the vastness of the universe is in the form of another cloud. From there, the new stars, the other kind of celestial bodies, celestial mechanisms trying to operate. So it is a rebirth. Everything is recycled in the space, because space is, as we understand right now, it's not leaking. So it's nothing is going out of because it's a ever-encompassing thing. Anyway, what I'm trying to tell was that not all the elements are formed together. This is how the heavier elements formed. This is how the smaller elements formed. And the same elements, iron, if you see, simply in this, the massive red supergiant, it is there in the core, the iron and nickel. The same iron that is present in your blood. Don't you feel yourself as a star then? You should feel, and we all feel. We are all same. If you start relating like that, where the sodium in my bone has come from, or calcium in my bone has come from, it's an interesting way of exploring the space also. The rest of the elements, what happened is that, so these kind of things happened, and long story short, Earth was formed. There are a lot of, how it was formed, or it's a very simple story. Anyway, the Earth was formed. Living beings coming into, life has started. We came into picture and we changed the whole picture. So we have come into picture and we have changed the whole picture. Then we start expanding the period. We understood the atom. We understood these fundamental things. We learned. Now I know the trick. That point we have reached. Then we start experimenting. Okay, I need to create more elements into that. So right now that, up to 108 or more elements are being made. They're stable, not stable. That questions are there. Most of them are not stable. If it is stable, it should have been formed earlier also. So how we are making, as human, in two places you will see this in the whole world. One is in nuclear reactors by nuclear fission, as you see in the right side picture. Other is a particle accelerators, that the equipments that we are established for studying the fundamental particles, or as you know, to find out the God particles, bosons. So in these two areas, still elements are being made. The rest of the things are still happening in the universe. If you see, any star, for example, that the element formation will be having a new magnesium coming, a new nickel is coming. The nickel never existed before. So the element creation is a continuous process which is happening in the universe as it expands. So that's why the whole elements, came into being. Now I'll just share with you some interesting slides, big things. When we look at the sun and try to understand what are the elements present in the sun, first of all, how we'll do it? We cannot go there and scoop a little bit of sun and come back and analyze it in our lab. It is done by the spectra of the elements. Spectra is the elements, that's the color of the elements. What we see is that a particular element is heated, given some energy, it will excite. Who will excite? Basically, the electrons are getting excited. And when it comes back, it releases that energy, and that particular energy corresponding to that, there's a wavelength, there's a color. Anyway, based on the spectra of the solar radiation, solar light and other, invisible part also, we know now that the elements observe the suns, what are they? And when you observe, we are, why silicon is still there? Sulfur, iron, okay. So what happened? Because sun has not come to a red giant. And I told that, iron will be forming, heavier elements will be forming when it is a red giant. So what happened? Then we know that the sun is not an original sun. it is like, it's not duplicate we call, it's like a recycled star. Some star had his, its life, it died to natural causes. Then the cloud was nebulae, whatever it is left behind has been recycled to form a star. So sun is not a first generation star that we know. So that's a fact, maybe we know, but it's a way that we found out, one of the way that we found out that he is not the original guy. Second thing is, elements not in the universe. If you see, hydrogen still there. No, a lot of the heavier things are only in a small. Or these things also it comes from the spectra of cosmic sources. So here also it's good. What I feel as a chemist is that a lot of hydrogen are still there to be converted to a bigger element. So we are not in the end of the universe. We are still in the starting. So it's hopeful. Still the concentration of the total concentration is less. It is very useful when you are looking for life elsewhere in the earth. We can compare it. Whenever the life is there, mostly in the way that we know the life made up of same material that we have, then we can look for the same elements elsewhere in the universe also. That's interesting. So if it is more, for example, if somebody is telling silicon is the maximum, the element which is most abundant in the universe, then I'll go, okay, there will be more earths, more people, more, because silicon is one of the major component. When we come to earth, silicon and oxygen and aluminum, are the toppers. And then, of course, we know the iron is the core mostly, and oxygen mostly in the water and in the air. And nitrogen is the main guy, again, in the gases that is not coming here. So this is a composition of the earth, as we know. And when we look in the composition of the earth, one thing fascinates me is that this hydrogen, helium, carbon, nitrogen, oxygen. I have just highlighted hydrogen, carbon, nitrogen, oxygen. Okay. These are basically less abundant than silicons. What happened? Why Earth is so enriched in silicon? We know that aluminosilicates and all are making the most of the earth that we know as a surface, going to some depth also. After that, it's iron and other metals come into play. But why these guys are more abundant? It's like, when your mother is cooking something, mixing something and giving you then you have more number of payasam, if you say, you have more number of cashew nuts in your thing than the others in that kind of stuff. So even though why it is more in earth, that's a question. But the other elements, aluminum, sodium, iron, calcium, magnesium are abundant. So what happened is that don't be panic. Actually, the earth is leaking. How it is leaking is another question. See, all these elements can form hydrides and oxides, which are very, very low boiling points, or basically gases in that way. So these kind of materials are getting converted into their hydrides and oxides. This happened at after a certain time after the earth cooled down. Anyway, but still happening. These elements, the problem with these elements are that these elements can leak out as their hydrides or oxides. So they are less abundant because Earth is having not 2000 years of history. It has very, very, very big history behind it. The way it is cooled, the way the atmosphere changed from, acidic in that way. So basically because of that, we have the change, difference in the abundance of materials. This is an interesting fact. This argon, all the chemists in the world use argon for inerting their reaction medium. Whenever we do a reaction, we don't want the reaction to react with air. So what we do, we pump in a lot of argon along with that. We know that this argon guy will not react with anybody. He's a sleepy guy. We know that, as we see in the picture, the electrons are filled. So he's a filled guy. He's a tummy filled guy. So he will not want more reaction. So, but this argon can also leak in the earth. To us own, scientific discussion happened. Thought which has come. But the thing is that argon is different. Is that argon is also produced by the radioactive decay from the isotopes of potassium. That's a small interesting fact. Iridium is another thing. Iridium was very less abundant in Earth, as we seen in the elemental thing. So, but why this iridium has come from we know that if iridium is there in good quantity somewhere found in Earth, we know that, oh, no, it is not from the Earth. It must have come from somewhere else. So that has happened when there was theories going on about how dinosaurs, extincted. Like there are dinosaurs, they are ruling, and one fine morning they are not there in the sense. So in that particular thing, this finding of iridium as a layer and iridium concentrated Earth was a major breakthrough. People know that this has happened years back, and this iridium must have come from asteroid. So, because finding of iridium was a major turning point in putting up the theory that dinosaurs' extinction was because of the asteroid impact. And now, when the Earth was formed, all the elements were there. Then, as humans, we started using these materials to support our lives. That was a major thing. Like, we can go around like, for example, a cat or a dog, without actually thinking about how to utilize the things or the materials for our better living. So we thought in that, we are a species who thought in that direction. We have transformed the materials, we have experimented with them, we have made tools out of it. And from a caveman, we have come to the present situation. We are still in a cave, but for a different reason. Most of the material that we consume today come from, for making that big industries are working, and most of the elements are digged from mines, big mines. So from a cave to the present day cave we came, and where we are going, if everything goes right, in maybe we will be settling down in extraterrestrial body, maybe Mars or wherever you want to be. But one of the propositions, one of the thought process in a habitat is a cave, because cave inside, you have seen the Martian movies or the movies also, a cave can protect you from harmful radiations outside, and it can equilibrate the temperature. So from a cave to a different planet is what we're going, and chemistry or material science is supporting the whole endeavor. It's playing along. Wherever there's a requirement is coming, we have done it. So one of the fine example for this is in our space exploration, and that I will come in the next chapter. She said, I'm continuing. Okay.
Yes, sir, please.
Okay. So let's move to the chapter 2, the present. We have come to present days. For this, we will be mostly very, you'll be knowing, you can Google it and find out in the sense, most of the things. But the idea what I am trying to bring in your mind is something else. That is, see, why we are venturing into space is a different question. Somebody tell it's a curiosity, somebody is because of, as you know, all this history, when you look at the rockets, started as a war equipment, then it has come after the World War, all the technology were there, and people started the what you call the Cold War time. You want to be over somebody's head, you want to observe them, you want to be in space. The space was not that much exactly understood as, deep space or going to moon or something. I want to be, put some camera above your head. That was the main idea. But then it grew into a scientific, interest, and everything grew, and the development happened. So everything has started as a rocket the Chinese have used, or the Tipu Sultan has used. There were the basic mechanisms operating, but then from the war to the basic utilization, to help the common people, kept finding new medicines, helping students reach out to their schools from remote areas. In that way, it has transformed. So the requirement for the whole thing, the space activities to flourish well, we have made some machines. That the machines what we call in space area is a rocket which carries the satellite or anything to space. Second is a satellite which has a lot of applications you are very clearly aware of. Third thing is another machine. I will call this a machine from the from as a chemist, I'll call it. But maybe the hardcore mechanical engineers or aerospace people may not call it. But anyway, this particular box has to come back was the question. Because anything they are sending, it is going out and is roaming around after its death. It is parked in its, retirement homes or is destroyed in a different orbit. So that's a life. Rocket, we know, right now we know reusable rockets are there, but else, before that we are all were, coming back or being burned in the atmospheres. But this particular box on the third is a space capsule. That's exactly photographs of a model that we are, as you are all aware, the Gaganyaan. This has to come back. It has to come back intact. It has to carry people, and the people should be alive when they come back. So this is more constrained, people involved. Okay, the first two machine doesn't involve many people. And when we talk about people, the third machine is a suit. But this is a dress, no? This is actually a shirt. This is why you call a machine? It's actually a machine. It's like a small home in the shape of a suit. So it protects you from the outside world. It gives you warmth. It gives you, feeds you. It checks you. It takes care of you. So it's actually a machine in the form of a clock. So these are the four machines that we are dealing with right now, at present, worldwide. One thing I missed maybe here is the International Space Station. That is a combination of, I would rather consider as a satellite kind of material. So a machine. So these are the machines that we are dealing with. And we know mostly for the GSLV, if you simply, this is the most common slide that we use wherever we go. So I'll just start by that. You know that in mass wise, if you see any rocket right now, on an average, it is taking say 79 or 80% or more than that sometimes for the propellants. Then only the remaining part is for the structures, 9% is other materials. The payload comes 1%. For carrying 1 gram, you have to carry 100 gram in that way. The vehicle will weigh 100 gram in that way. So what I'm telling is that the weight percentage, the fuel rocket is one particular machine what we use as, higher weight percentage of fuel. If you look at the car, it may be 3% or something. If you see an aeroplane, it may be 40% of the fuel weight percentage, maybe. But it's one of the, fuel is not that much like Maruti car. It drinks a lot of fuel. So the point is here is that the whole thing has to be made. The propellant has to be made. The structure, which is basically mostly metallic, now composite materials and class of materials are also coming up. The other materials are used as, to tie something, to join something, to coat something, coatings, that kind of a material. Then comes the payload. Of course, you know that the satellite also is made up of a lot of different kinds of materials. So all these materials are existing naturally on Earth? No, never. Like we build our houses. So we have to make it. So this is how the material a scientist comes in the picture. If you see the role of a material scientist that I represent from my fraternity, there we have two types of people working together in ISRO. If you see engineer and scientist. Engineers are the people who make the design, they know the physics, they know the mechanics. If you compare it with the way that we are making a house, the engineer, the masons who are making it, mostly in our area, in my house, when it was built also at the day we are stepping into a new home, we call all these people, give some good cloth, new cloth and money, that kind of customs are there. So who are the people who are making it. But how many of you have thought about calling the person who's made the brick, who's made the cement, who has, the sand is not made, it is collected from somewhere. So these people are never coming into picture in the sense that that's the way that it works. But the point here I'm telling is that the material people who are working along with engineers to make our space dreams come true are working on some aspects. In a triangle, this is a very famous triangle about material science. In that, when a person is asking for the requirement of a material, for example, I need a brick, he'll be telling, the brick has to take, the two floors I have to make, the brick has to be strong. So he'll tell that it's strong. So how a brick maker will make it strong? He will select the clay, he will make sure that the green clays are made, that the green with the mud, they are made without any impurities inside, any leaf or dead leaves or rocks or something is inside. Then he will make sure that it is heated up to a particular temperature so that it's baked to the red color, that iron color what you're seeing. And it has good sound coming out of it. So if you see in the same angle, the same scenario or same way only we are making the materials for space anywhere when a material is being developed. So we are finding out the relationship between the structure and properties. By knocking in the brick, people know that, okay, this is a good quality brick. The sound will be different. The metallic sound will come. So he's actually thinking, or actually he's looking into the relationship between the structure and its properties. It's kind of a non-destructive testing in our terms we call. Then the way it is processing, as I told you, the processing without impurities and all those, without any leaves getting into the brick, that thing is there. And if it is there, it will break because that leaf is there, there will be a hole, and when we are pressed, it will crack from the hole, that particular impurity area or something. So there is a connection between processing and property. This is what we usually do in our, when we are asked to bring about two materials. This is the same thing what you people also, I just want to tell you that even if maybe the people, some people from are coming and so much enthusiastic and coming, and I want to become a material scientist. For example, if Thangalashmi want to be a material scientist, I think Thangalashmi is there, or Rifa Fatima, anybody. So when you people want to become a material scientist, this is what you are supposed to do. You want to, for making all these things, you should have a very good understanding about the materials. But the challenges will be not like building a house. It's something different. I will tell you three major things. The first picture is about a lightweight thing. It is getting supported on a very flimsy kind of a flower or something. Second thing is a metal being corroded. Something is happening, like a metal corrosion, something is happening, the type of corrosion. Third thing is extreme heat that we never experience, or usually we experience that the maximum temperature we experience in our lifetimes. Maybe we are having fever. No, when we are going close to our kitchen burner or something, or sometimes in big factories where the iron is getting melted and all those things. But there are all, we have options for the people to be away from that. For example, in a metal industry, everything can be robotic. You need not go near to that. But a person has to come back to earth. The earth to show, with a lot of passion, it tries to stop that. In that way, if you look at, a lot of energy is getting, released as heat, and also we have to make materials which sustain the temperatures. So basic three things are the conflicting demands. One thing is we need a very high strength, okay, but we cannot take much mass. You're seeing the big structures being made. If you want more strength, usually the normal thing people add is more material into that. But that is not going to work here because you have to fly. You know that 90% is fuel is required for taking 1% of that in that range. And if you add anything more, that's not good. But then the demand is coming like that. It's conflicting in the normal way. It's conflicting in the sense that the high strength is required. Okay, sir, we'll make a high strength material. Okay, the demand. No, it has to be very low mass. Okay, how we can make it? Second thing is the space grade is a different grade. Okay, apart from a lot of parameters are there anyway. But the important thing is that it should have low total mass loss. What is that? See, when you get into your car on a very sunny day, you feel that if it's a new car, or you will feel the smell of some, chemicals, some solvents coming from the seat cover, coming from the bonnet. That's because all these are polymers cured and set. But at certain circumstances with a high temperature or something like that, some volatiles, what we call volatile, very small molecules will come out of it because that polymer has not completely cured, or it has a tendency to degrade to some level. That is completely not acceptable in the space criteria because the number of atoms otherwise also in the space is less. We don't want to add more into that. Okay, and in a wrong way. Next guy who is in question is atomic oxygen. I don't know whether you have heard about it. Right now, when you live in Earth, you have all the oxygen. When you have trying to reach space, in between there something magical happens. The oxygen atoms get splits into two, and it is O atom. Oh, then people ask, the O atom cannot exist. No, from the chemistry we know that it has to satisfy its valency, and it has to combine and form a molecule. No, under those circumstances, you can read about it. I'm not explaining it, but this atomic oxygen is a very naughty guy. We know that the normal oxygen molecule will react with the metal and corrode our household utensil or anything. Like if it is iron, if it is not steel, it will corrode. But atomic oxygen is a step further. It's highly reactive. This guy cannot make a molecule, and is highly energetic. He will attack anything coming to that. Basically, what is happening is oxidation. So we need good coatings to protect it from atomic oxygen. This kind of things never exist in our normal, earthly living, in the sense that on the surface of the earth. Third thing is a very low and very high temperatures. We know about the very low temperatures of the space. We know it may go up to the in the normal boiling, freezing point of liquefying point of oxygen or something. But still, it doesn't happen because the space is back up. Anyway, the point is that, and when it comes back, the space capsule is coming back. It has to protect itself from the high heat. So the temperature range is very high. So these are the main factors in a normal way. We keep in our mind when we develop a material for the base core of the thing is that the basic challenge for a material chemist or material scientist or material engineer is that they are conflicting. Most of the things are conflicting. You want that, the conflicting properties we call. A particular fruit you want with salt and sugar will be different to get in nature, no? Normally. The conflicting demands. So that kind of thing you will be, that's a challenge that you are having. And this is a small slide, you don't worry about that. I'll just list some materials. If you try to classify the whole material, it's a big list, a very big list. If you try to classify it for our understanding, I just classified into 6 categories. First thing is the energetic materials. These are the guys who is having a lot of energy and they are used as propellants. You just tickle it, just make him oxidize, make him combust. It will release a huge amount of energy. These are the materials who store a good amount of energy in their chemical bonds. And it is released when it is decomposed, or oxidized, or whichever way it is getting transformed. So these are required for the propulsions, for the rocket to fly. Second are metals and alloy. We know a rocket is basically made of metals. There are material scientists working on finding out, metals which are lightweight but having good strength. Then metals which resist some corrosion, that way. So metals are the second materials. We know metals we are very much clear about. We see every day in our life. But energetic material we not see every day in our life except in Diwali or, some movies are getting released. Anyway, third material is polymers. We know polymers. We know polythene cover. We know how the polymers, the plastic bottles and everything. A variety of polymers. You can number it, but it's a huge number. I'm not doing that. These are used in different areas for joining pieces together as coatings on metals or as vibration isolators or something. Third thing, next is a ceramic material. This is the area that I will be putting that now because that's the material that I'm working on. These are the high temperature guys, which will not melt when a metal is melted. So when the metal stops its run by melting, when we are increasing the temperature, first, usually what will happen? The polymers are 500, 700 degrees Celsius, the polymers will burn. After that also the metal will be there. That's why we are using metals as, utensils, cooking utensils or in crucibles or something. So after some time, even 1500, 1200 starting from, there's a range. Metals also give because that reaches the melting point of metals. Then after that, who is there? The answer is a ceramic material. Ceramic materials are there right now, which you can go without decomposition even up to 3000 degrees Celsius. These are the high temperature guys. But ceramic is also a problem. You must have broken a lot of ceramic cups in your house. You know that ceramic materials are very brittle. So there is a story in that. I'll just come to that. How we are making ceramic non-brittle. So the answer is a composite material. the question, the one thing I just want to tell here is the first question. What do water and aluminium have in common? If your answer is like something like that, okay, I take water in an aluminium pot or something. Okay, that's an answer, but that's not the answer I intend to be. That is something like this, generating energy. So this is actually an internal combustion engine, like in a car, where the energy is getting released. But the case of a rocket is different, now you know. So in the case of a rocket, particularly in Gaganyaan, when the Gaganyaan is flying, you know that water is making Gaganyaan fly. A part is played by simple or water. How it comes? Maybe you know, you've seen these pictures in the newspapers. You know that the cryo engine, CE20, is a cryo engine. Why it's a cryogenic engine is because what is happening inside that, it is hydrogen is getting combusted. Hydrogen is oxidizing or combusting to form water, which is a superheated steam with a lot of energy. This energy is only propelling the cryo engine. So when water is getting formed, that particular reaction can be used for these kind of propulsion applications. We simply call it as a cryo engine, but so simple. We know the hydrogen, we know how oxygen is every day, very simple molecules, but they combine together to form water. This much energy is getting released. This much amount of water vapors are getting produced, and under that temperature, it expands through the nozzle that pushes the rocket forward. So this is how the water is making the Gaganyaan fly. One more interesting thing is that this liquid oxygen, we call it LOX, liquid hydrogen, LH2 we call. This has to be, if it is stored gas, you need very big storage tanks. So it has to be pressurized. It has to be pressurized and it has to be liquefied. And to keep it in that particular temperature, you have to keep it at very low temperatures, minus 183 degrees Celsius and minus 250 degrees Celsius, respectively. This is one of the major thing we had. The major difficulty with the cryo is to handle these materials at these low temperatures. Second thing is how aluminum is helping us to escape the earth. You know this is LVM3. Who is actually helping us to escape first from the launch pad? I just want to leave the launch pad. These are these two boosters, what we call S200. And I'll just show you on video or from the onboard camera. This is how it leaves Shar. You see the the island of Shar behind the coastlines. So what is happening here now? After it just help the rocket to escape the launch pad, escape the whole initial gravity. So after that it leaves, and then the next phase takes up. So what is the basics behind that? Who is helping that? Aluminium. Okay, what aluminium is doing there? What aluminium is doing, the answer is here.
A sample of pure aluminium powder is placed in the flask, which has a small exhaust hole in it. Oxygen is passed through the flask, and the aluminium powder is warmed with a Bunsen flame to initiate the reaction.
You just see what is happening to the glass. Sorry.
The aluminium powder ignites, and the reaction is highly exothermic. The heat generated by the reaction melts the glass flask. Aluminium burns with a bright white flame similar to that of magnesium. Aluminium foil or wire will not burn as easily. The large surface area of the powder encourages it to oxidize more rapidly.
You heard two things here. What is that aluminium oxidizes? It's an exothermic reaction. Simply what it means that it gives out a lot of heat. Oh, that's good. We can use that heat for expanding a gas which will expand through the nozzle and push the rocket. Second thing is that you don't feel that okay, then I should be very careful about using the aluminium utensils in my house. So the second point what was told in this video is also that we take very good surface area, so that surface area has to be increased. So to increase the surface area, you have to powder it. So that's a way we are using very fine aluminium powders, and the temperatures are very high. So this is a way that aluminium oxidation is creating a lot of heat, which is used to expand gases and thrust to the rocket. So this is a role of aluminium. basically. This is a simple, I'm not really much on that. What you see first is the composition of a normal solid propellant where aluminum is there, some binders are there, don't worry about that. But one guy, the maximum is not aluminum. If you see 68% is something called AP. AP stands for ammonium perchlorate. The structure is given here, don't be worried about the structure, but you can see that lot of oxygen is there. So when this ammonium perchlorate is decomposing, it releases a lot of oxygen. So that's a basic source of oxygen for the aluminum to oxidize. And as an additional help, this ammonium perchlorate also oxidize or decompose exothermically. That also will generate a lot of heat. So this heat plus this oxygen will oxidize aluminum, and that only is providing the thrust. To start the engine, as you see from the animation, you can see that an initial ignition is happening just to start the decomposition of the ammonium perchlorate. All these things are mixed together. We use a binder, kind of an adhesive thing, what we call as HTPB. It is an hydroxy terminated polybutadiene. It's a very very old composition, very robust composition. And the middle video is where how that propellant is getting cast. All these mixtures are mixed together. The basic thing I am telling here is that aluminium oxidation has this much potential. There is normal aluminum, which is also abundant material on our surface. We know that it is highly reactive because normal aluminum utensils will have a layer of aluminum oxide. Malayalam we call klav. Maybe there will be different names in different areas, but it oxidizes. So that simple thing is used in a entirely different purpose. And without aluminum, can you think about? We cannot think about launching a rocket, escaping the. Excuse me. Hello. Hello. Oh, okay. Okay. I'm audible now, sir. I think I'm taking some more time here. Okay. Okay. That's a problem with these online meetings, no? Otherwise, if we are in the middle of the student, we will have always this feedback. Okay. So I'll just continue. Now we know that simply how this a simple aluminum that we use every day in our life is actually helping our rockets to fly, to escape the gravity. Third thing, this is a little bit complicated. Try to make it simple. This is the role of nitrogen. I've just told you about the water, what it is doing, aluminum. Now it is coming to nitrogen. This guy is the element that I like personally is nitrogen because of the abundance. If you have a national bird like the national element or something like, just till nitrogen, because from the type of compounds that exist to the energy that is the nitrogen bonds are keeping inside them, lot of use. We cannot think actually without even water, but not nitrogen, I would say, even the life sciences. So what happens here is that hydrogen, a particular type of liquid, which is having a melting point of 2. And this will decompose and produce nitrogen and hydrogen. Reaction 1. Reaction, it also decomposes through reaction 2 in a particular way. And there is a third reaction where this ammonia is actually recombining with the original hydrazine forming something. These three reactions are very much importance because these particular reactions are the basis of what we call as liquid propulsion. Simply, these nitrogen compounds, when it decomposes, two things are happening. One thing is it is creating some more molecules. One molecule of N2H4 in the reaction 1 is making 3 molecules of a gas. So it is basically there is an expansion. Number of molecules are higher. So that is good, no? For the propulsion, that an expansion is good. And it's also an exothermic. Both reaction 1 and 2 are exothermic. But at the same time, the reaction 3rd is a counterproductive guy. This reaction is actually an endothermic. It is actually taking away all the heat It is not doing any good, but we cannot avoid it in the case of hydrazine. So when this issue has come, when the problem has come into the chemical people, chemistry people, material scientists, what they have done now, they have simply put ethyl group at the end of nitrogen. Case gone. So third reaction will not happen. Okay. See the beauty. You simply put how we are putting is about the chemical reactions when you learn, when you are getting experience. It's an easy job. But the thought process which has gone in is what I want you to take a note about. The additional advantage what we got here, apart from, we are removing a heat removing mechanism or endothermic mechanism, is that the melting point has still gone to minus 57. That means even at lower temperatures, this unsymmetrical dimethyl hydrazine will be a liquid. That's an added advantage, because if you are taking filling the hydrazine, you are putting it in very polar regions and in a very winter time, it is not pumping out because 2 degrees Celsius and it's frozen to solid. That problem will not be there. So that's why how chemistry is used to solve problems related to the propulsion, particularly liquid propulsion. This another compound is here is a nitrogen oxide. Nitrogen oxide changes color with its structure. You can simply see that the brown color is for nitrogen tetroxide, nitrogen dioxide is white color. This is a very interesting thing, but I'm not dwelling much into that. My point here was that when this particular nitrogen dioxide, the role is to supply oxygen. Okay, and this particular nitrogen dioxide is added along with the hydrazine. When these two people are meeting together, some magic thing happened that I'll tell you. But before that, there was an issue with the nitrogen oxide. The issue is that this nitrogen oxide, when it is filled in a tank, which is usually made up of titanium alloy or something, it is creating nitrates on the surface of metal. It is creating problems to the strength of the tank. What we call is a stress corrosion usually. So to solve that, this issue has come. So what chemist has done, they have basically mixed one more guy into that, NO. Okay, it's like in the schools, people, when people are talking, teacher will put to the most, obedient guy in the school, the class, and ask them to take a note of who is talking. In that way, nitric oxide is put into the play. When the nitric oxide is coming, it simply reacts with the nitrogen dioxide and forming what is called N2O3, dinitrogen trioxide. This guy will not react to form nitrates and it will not cause the stress corrosion. So simply, if you call simple, it's simple. Simply by addition of a molecule or nitrous oxide, we have solved the problem of stress cracking. And one more thing happened is that, beautifully the color has changed. I love the blue color more than that. So this mixture of nitric oxide and all those things are called MON. MON 3, like that, normally we call, because of the composition is 3% nitric oxide. Anyway, this is how these two compounds of nitrogen for its high energy content are tweaked for our actual application. One is used as a fuel, other is oxidizer. And as I told you before, what is happening when we mix these things together is what is called hypergolic. They simply come in contact, they ignite. There is no igniter required. When you stop the pumping of these two tanks, you are storing liquid fuel in one, liquid oxidizer in one. When you close the valve, engine stops. When you open the valve, again the engine starts. It's not like starting a solid engine. We don't require any starter because these two guys are extremely energetic. The moment they come in contact with one another, they catch, they combust and generate a lot of gases and pressure. The third material I just want to, so we now know this aluminum, nitrogen. Now carbon we cannot leave behind. Now carbon, when I looked at, one of the important applications is that we have made carbon, we have seen carbon as graphite or something, but carbon is being made into a liquid form. We have to make it as a phenol. Then you have to make a phenol formaldehyde out of it, some reactions. Don't be worried about the structure. We have a liquid material full of carbon. What it is basically useful for? If you burn it, if you heat it, what is happening is that this basic carbon material will decompose, as you can see on the left side. It will decompose to carbon, hydrogen, hydrocarbons, water, and everything. It will come out. Okay, that we know. If you burn wood, it is happening. Carbon is burning. So this particular thing is doing on, unseen mechanism is operating here. What is happening here? A particular amount of heat is given to this carbon material. It is taking that. And it is decomposing. When it is decomposing, it is actually some volatiles or small molecules are going out of the system. These molecules are actually taking out a lot of heat from the substrate. So it is removing heat from the basic material which is getting charred. So whatever is getting charred, the molecules which is coming out is taking away the heat. Somebody has put a good thought on this. And right now, if you know, this basic mechanism is used in almost all thermal protection systems, the basic thermal protection systems in the world. In a nozzle, if you want to protect, a carbon material is put. When the basic mechanism or the operation scientific terms, it is called ablation. When a carbon material ablates, it takes away heat and protects the background structure. So basically, you know how carbon is playing a big role. Why we have made it as a liquid is that for its easy decomposition into such a small molecules. If it is a graphite material right now, as a whole graphite, carbon alone we are putting, it will apply to carbon monoxide, carbon dioxide, but here we have more options for its decompositions, and the volatile products will take away the heat. This is the way carbon is protecting us. Towards the future, when you look, I just will glance through that. We are looking for re-entry missions, reusable launch vehicles, and hypersonic vehicles where we need very high temperature materials. So these abilities will not work to some extent, because if you want a higher temperature reduction, you want a very big, you have to make, thicker blocks. So that is not good for the design of the, flight of the rocket. So we need alternate materials. As I told you before, the ceramics are the answers for that. The type of ceramics I am talking about is called the carbides, nitrides, and borides of carbon and silicon types. The highest melting point we can see here. If you see, graphite is also good. No, graphite, you see, it is having a melting point above 3,500 degrees Celsius. Then hafnium carbide and tantalum carbide, the material, type of material that I actually work on, is also equally good. Then why can't you use graphite? It's easy, to make and all. But the problem is that graphite in the presence of oxygen will simply get converted into carbon dioxide. It will not be stable. But in the case of a hafnium carbide, tantalum carbide ceramics, it will form its oxides, hafnium oxides and tantalum oxide, which will actually protect the substrate. So this is a basic mechanism for the use of high temperature ceramics as thermal protection materials in our space programs. So just keep that in mind. This I'm skipping now. Anyway, one thing is that we know that these ceramic materials are highly brittle, as I told in the introductory slide. We have to solve this problem. How we are solving it in the same similar way that we are constructing a house. When we are constructing a house, you know that the beams, how the beams are being made, we are putting metallic rods inside and then pouring the concrete over that. So the metallic rods will take care of the tensile loads, as we call. The other person will take care of the protection and the compression. In the same way, the ceramic, the type of ceramic, we are right now reinforcing that ceramics with the fibers, not with the metallic fibers, but with the carbon and silicon carbide fibers. This is an emerging area of materials, what we call as ceramic matrix composites, for which the activities that we are as a team in VSSC, we are actually making these materials. And if you see, these kind of materials are being used for Buran, which is a re-entry vehicle from Russia. And Rafael, the type of jets that we are buying and in the engine exhaust area also, they are using the composite materials. So these composite materials, ceramic composite materials, are a step ahead of the ablatives in the sense that it is stable and it is not brittle, in the sense that because it is reinforced with the carbon fibers. So this is basically an overview of the type of materials right now we are using. And I have a small chapter on the future. Can I, sir, I'm taking much time, or shall I? Oh, okay, I just because one more chapter is there for the conclusion. I'll just brush through that. I'm afraid I'm taking a lot of time from. Okay, thank you. So let's move on to chapter 3. I think people are all there and not bored, I suppose. Anyway, anyway, I'll continue to chapter 3. This is about future, so nothing, but it's not. Most of the things are the startups or what we call the initiatives that the worldwide people are taking, and why we are looking in that aspect, I'll tell you. The title of the chapter is Imagining Without G. You see that the G is a capital G, it's not a small g. What's the difference between the capital G and small g? I think you are aware. I will just tell you. The small g is the acceleration to gravity. Whenever thing is, falling into Earth, it accelerates, and there's a rate for that acceleration constant. That is only with respect to Earth, and it actually changes from location to location. The G is a gravitational constant. You must have derived the relationship. Maybe, I don't know, that thing is there in that high school or in +2. The deriving the relationship between the big G and small g. The big G is a gravitational constant. It is a universal constant. It is about how two massive bodies attract each other and the type of energy in between them. So it's a constant. So when we talk about space, we normally don't talk about the small g, which is actually an earthly thing. We talk about g. And we have to start imagining about the materials processing without gravity. Then we understand that most of our process in which a material is being made, gravity, even though we are not talking about it anywhere, we are telling that you mix A, mix B, heat it to that temperature, that pressure, you get C. In that way, equations are being made. Never a term of G or found, no, because anyway, that is a constant in it. But when we move out of it, move out of the realms of gravity, G, small g, Earth, we found that this G is having a profound influence on which how the chemical reactions are happening, how the crystallization is happening, how the materials are being, interacting with the materials and all. So a lot of things are there. So that's the interesting part that I request to you in your future endeavors, or in the when you study more also, you should be more interested. Keep an eye on that, the effect of G on things. You keep asking questions about what will be the fate of this particular reaction if G is not there. In that way, just to ignite you on that particular thing. We know that the conditions are different. We know that space is high vacuum. Vacuum is about the number of particles in unit space. Okay, if you have a low number of particles, you have to pick and throw out the atoms from a box. You start picking up atoms and throw out of a box. You create vacuum. That's the way vacuum pumps are working. Then microgravity, you know that we have gravity in LEO, particularly in the low Earth orbit where the International Space Station is there, we have microgravity. But on our planets or terrestrial surfaces, we have slightly higher gravity because of the material. Temperature also, we have very low temperatures in space. But in Earth, we have -88 to 58. 58 was recorded in a desert in Libya. 58, okay, and -88 degrees, the lowest temperature was recorded somewhere in Antarctica, some of the stations that we have, the Vostok station, I understand. Anyway, this range will already exist in our surface of the Earth to some extent. If you go deeper, it will be different, simply. Anyway, these are the difference when you do a chemical reaction in space and Earth. These conditions are different. Along with the International Space Station, the Russian or the Chinese, or what we are coming up with our Bharatiya Antarisha Space Station also, the basic thing, all the experiments right now are happening or planning to be held in these space stations. That you should understand. We should have a module where all our chemical reactions or new material reactions will be done. Some interesting facts I will tell you about that. The first thing is a spherical flame. If you see, a flame lit on space has come to a spherical shape. Was the first interesting thing happened. In the sense, not the first time telling, one of the interesting happened. Why this flame is spherical, you should be wondering. And when we look at our normal flame on Earth, it is having that particular shape, the conical shape. That is because of the convective heat transfer. What we call is that heat, that hot rises, and in the bottom place where that becoming empty, the cold gases come and fill. So always the movement is upwards. So that is only creating the shape of a flame, basically. And when there is not a gravity-induced convective force, like the gravity plays a major role in this kind of a fluid flow, or in the case of this kind of a convective flow. When the gravity is not there, such kind of flow is not there, and there is no reason the flame has to be that particular shape, no? So because of that, the flames are actually, it's a very interesting thing. The flames are actually spherical. And the suit, the black suit what we form usually, that was very high in the space flights, because the conversion of this particular fuel, the hydrocarbon fuel, to carbon dioxide and water is not complete. It is stopped in between. And mostly the product of combustion in space is a molecule called formaldehyde. This is a bigger molecule that is actually creating a lot of soot. So a lot of soot is getting formed. That's another difference in the when a flame is being lit there. It is spherical, as I told, and it is cool. This cool thing is very interesting because the flame temperature was so low. Usually, if 1200 degrees Celsius, a normal flame, hydrocarbon flame goes, this kind of flames, when lit in space, first if it is having a normal flame, then it goes down, it dies down, then there is a flame called a cold flame. This cold flame is actually very much important because it has giving some clues about the combustion process, how to make our combustion process on Earth, more environmental friendly and all. So these studies are being done there so that the input what we are getting from the space studies, we can use it for bettering our lives on Earth. That's the basic.
Williams and colleagues were doing a space station experiment called FLEX to learn how to put out fires in microgravity when they came across something odd. Small droplets of heptane were burning inside the FLEX combustion chamber. As planned, the flames went out, but unexpectedly the droplets of fuel continued burning. That's right, burning without flames, says Williams. At first we didn't believe it ourselves. In fact, Williams believes the flames are there, just too faint to see. These are cool flames, he explains.
Well, this was important because the flames are different in space, but the experiment was conducted to check how much fire hazard is there, inside space. If some fire is happening inside crew modules and all, what will happen? Second word I just want you to keep in your mind in your pursuit of knowledge in the coming years, or when you study more, is the way that we do chemistry, the chemical reaction. We take a RB flask, put the reactants, react, take out that. So this kind of a reaction is called a normal batch process. One by one batch, next batch we'll do. But this kind of a reaction has a lot of difficulties in space with respect to the storage of the chemicals, the feeding of the chemicals, and controlling the parameters. So right now, work has started quite a little bit earlier also, but the work on flow chemistry, the reactions happening in a flow, the fluids will be flowing in a tube where the reaction conditions will be given. It will be heated up, some radiation will be given. But if you feel that, okay, this is going through a pipe that is in two bottles, but a lot of things are different. A lot of studies are yet to be done to understand, because if you want to make a material in space, flow chemistry is the way that we need to master for making the material. It has a lot of advantages, I'm not going to that, because without gravity, the flow will be a big problem. It will not flow. The normal flows in chemistry happens via gravity. Otherwise, it has to be pressure flow or something. Anyway, the flow chemistry, you keep the word in mind and explore a little bit more. The third thing is about our health and the type of medicines and the proteins. The way that we make proteins, from starting from Corona onwards, we are being very fastly developing medicines based on proteins. We have different kinds of proteins, and the protein synthesis in space is one of the major area that active work is going on, and still further work has to be done. If you see the two photographs, one is made in space, one is made in Earth, the type of protein crystals. The first one is in space, Earth, the second one is in microgravity. The major difference here is the absence of buoyancy forces. Buoyancy, gravity and buoyancy are playing a major role. The opposite actions they are doing in normal crystallization process. When a crystal is formed, when the weight is more than a particular weight, it will go down into the liquid part. So that kind of a problem is not there when we are doing the experiment in space, and the crystals will grow more uniformly, more clearly. But one thing is that it will be slow, because the process, the material transport will be low in space. So the process will be slow, but it will be steady, and we'll be very good quality protein crystals. So these experiments are one area in the biological point. Second is a tissue growth. Tissue growth also are the experiments happening in space. Here the competition is between gravity and intracellular force. Normally a cell grows in our body, in any body. There is a tug of war between the intracellular forces and the gravity. So the intracellular forces will win over gravity. Mostly the gravity wins over in the case of terrestrial tissue growths. Anyway, I don't have much expertise on that, but what I understood is that the cell formation, tissue formation in space can answer a lot of our questions in treating medicine, creating new medicines, in doing a lot of experiments in this space for when we are going and settling down in space. All these things will come into play, and in understanding how a cell grows, how a tissue grows, the basic fundamental thing, without the interruptions from the gravity, we can study. So we know. So this is another area. Then this is a fiber. I just want to put that this is an optical fiber. We know optical fibers. Most of people have seen in lights and all. But there's a problem for high quality optical fibers. It will have, as you see in the second photograph, a lot of voids are getting formed. But when it is formed in space, it is without void. So good quality optical fibers for information transmitting and everything is that atoms are being made, and it is Z-band fibers. It contains a lot of chemicals. It is written down there. The point is that in the absence of gravity, the materials are made without flaws. That's the underlined word. The flawless materials can be made in space, particularly not for regular use or not for very common use, but for very high-end applications. Metallic glass is the one word. I'm just not dwelling much onto that, because the metallic glass, this is interesting, because metallic glass is not glass and metal mixed together. It's usually all the metals, when we handle a metal, it's a crystalline metal. All the atoms are packed properly, neatly, utilizing the minimum required amount of space. So that's a crystalline material. What we're trying to make is a type of metal which is not crystallizing. So normally in earth conditions it may crystallize, but the conditions prevailing in space will delay the crystallization process, and it is possible to make a metallic glass material, which is not possible on Earth. So this is also a very interesting area of exploration. And electronic application wafers, I'm not dwelling much on that, but simply I'll tell you that so far, the type of material not being made in space, if you just see, these covetic materials are nothing but up to 2000, most of the research was on covetic material. This is nothing but carbon-added metals, in simple terms. 2001 to 14, lot of work on ceramics and silicon carbide wafers for our chip applications were done. These are all materials made in space. This has helped in understanding the basic mechanism without G. This has helped to make a better material without the flaws. These are the two major advantages of making it in space. And once you make it in space, where it is being used, simply on statistics are available in the net. I just put it across. Most of the materials in these classes, the blue lines are for use back in Earth. So these materials can be made in space and brought back to Earth for use. A second amount of that graph shows the number of materials being made. So mostly the space food and large waste structures, if you see that is for the space use. You make it in space, use it in space. The surface means surface of any lunar surface or Mars surface. So the materials being made in space are having applications on Earth as a material, as a commodity, or in understanding the basic mechanisms, or it can be used directly, made in space and used in space also, or can be used on the surface of other planets. I'm just telling you this. Keep in mind this word ISRO. ISRO is not a fancy name for ISRO or something. ISRO is for Institute of Resource Utilization. If you are going and landing in Mars or lunar, you have to make use of the material available there and make. So new chemistry starts. The adventure awaits you people. If you are going in the direction of a material scientist, is that when you settle down in Mars or lunar surfaces, you have to we cannot, it will be very highly costly, taking material from here to there. Like when we are going on tour, we take food and water. No, that we cannot take, it will be costly. So finally, the cost-effective and sustainable method will be to use the materials available on the surface of planets or satellites in the case of Moon. So that kind of an approach is called in situ resource utilization. So all these future locations are awaiting the future material scientists, as I would say. You have to start a new chemistry there. You have to start making materials in their lab. The time is very nearby. So you should start preparing for that. Just to inspire you on all these things, I don't know how many of you have seen this photograph. The importance of this photograph is that a high school student, Judith Miles, in 1972 has proposed to do an experiment in that time US space station called Skylab. What she wanted to study was very interesting. You think what we'll think about what high school student can have such programs. It is possible because her idea was novel in the sense that she wanted to study how a spider is making a web is differing from Earth and space. So she wanted to make the spider web in the international, so in not international civilization, the Skylab there. So very interesting thing has come out of this study. You can just Google it and you should read it. I was amazed by the fact that this proposal has come from a high school student, and it has actually brought some light into how this spider is actually understanding gravity and light, how it is perceiving Earth, like most of how he is making a three-dimensional location for making that. So a lot of anyway, the initial studies were proven a little bit only given so much less data, but the studies because of the fact that she has come with a novel idea is quite amazing. And with that, I'll just go to the final slides. I just want to tell you that the stories, past, present, and the future, what I shown you, maybe not be the future, because future is ever changing. I cannot predict it because the way in which it is going. So I am also don't know what will be the challenges for the material chemist in future. But from the understanding right now what we are having, we have to imagine the chemistry without G. We have to start imagining doing the reactions outside the realm of Earth, utilizing the materials outside the Earth. So it is simply your turn. You can go in a lot of ways. Don't be worried about this name of the materials, but we have to, actually the whole world is waiting for you people to come out with the solutions that for making materials in space, starting from when we start colonizing Mars and other extraterrestrial platforms. You have to study that all these things will change. The way that we'll learn chemistry, astrochemistry, chemical, everything will change. Mostly the scientific areas will merge together to form new ways of study. So be ready for these changes. Be ready to take up those challenges, because the chemistry and the material world is going to be different. You can do it because I believe, as I told in the initial slide, we are all stars, not Mohanlal, Mammootty, alone stars or Shahrukh. We are all stars because we are all made up of star stuff. Our bodies are made of star stuff. This is famous statement from Carl Sagan, who has ignited our minds with the science of type of science fiction that he has spoken and written. We know that, from the figure, you can see that you have 73% exploding massive stars. That percentage, the type of material in stars, in Earth, and your body is all same. And you are all stars. And I am looking forward for a better future with such ignited minds. And thank you. I've taken some more time, but thank you very much. And this is at the end of my presentation. That's all, sir. Hello? Yes, sir. I completed my presentation, sir. Sorry for taking a little bit more time on that. You're audible, sir.
Yeah. Yeah. Am I audible, sir, actually? Yeah. I was listening to Dr. Sreejith's presentation, who is a very close friend of mine. And I think he has taken a very right approach. You know, when we start a particular topic, you don't directly jump into that subject head along. And he has given a very, very nice introduction by a start. When we are talking about chemistry, we have started from the elements itself. And just like a story, he has introduced how it all started, how it has all evolved. Then he gradually nudged this audience to the specific applications and to both past, present, and future. So whoever is present, I hope it would have been an excellent introduction to the topic. And what Sreejith wanted, I'm sure, is to ignite, like he has pointed out in the end, create a curiosity, create an interest in the subject. Because even if you take 1 or 2, 3 hours, it's extremely difficult to properly communicate the complexity and beauty of the subject. But it is good enough to initiate the students into the topic, initiate and generate an interest, and for which I think Dr. Sreejith is extremely successful. So I have seen a lot of students have written questions in the comment box. And if they are there, they can directly ask, or someone can read it out so that he can answer all those questions. So I hope that each and every students have been immensely benefited. Not just the students. In fact, I also learned a lot of many new things from this discussion. Like each and every one of us would have gained at least something new. In that case, this would have been really fruitful. That's also.
Hello, sir. Am I audible?
Yes. Yes, Devananda. Yes.
Okay, sir. So, good evening, everyone. My name is Devananda Sreejith, and I am a student of class 9 of Vanchadyashram Selembra, and I'm standing before you today to moderate the Q&A session. And before getting into it, sir, I must say your session was really intriguing. And with what you've said at the end, I truly believe that we all are stars fashioned into flesh and bones. And thank you so much for being here with us today. So we've got many questions waiting for you. And let's get into the questions. So the first question is from Zehra Shamaz of class 9th. And the question is, how did we recognize and realize that hydrogen and helium, etc., are part of a star?
Okay. Because how we know that hydrogen exists in a star?
Yep.
Oh, that's simply, in fact, I have it all in between. We cannot actually go to star and do a sample and do some analysis there. Whatever it's possible is to have the light coming from there, and the light with a lot of existing spectroscopes or kind of cameras what we have, we know the spectrum from an element. So this is very unique, like our fingerprint. The spectrum of an element is so unique. So when we get the light from a particular star, we split it into its components, and each component will be looked for the signature of a particular element. So basically, from the light, we split and we check for signatures of hydrogen. The hydrogen spectra, if you Google it, or if you maybe in the school you studied, that's so unique. So if you see that spectra, you know that from the stars, that from actually the star, the hydrogen is there or not. So that's the way normal. Yeah.
Okay, sir. So moving on to the next question. We've got, she's asking another question. How did we recognize and realize that hydrogen and helium are a part of a star, which you've already answered? So moving on to Gautam Krishna. The question is, how do we detect the generation of a star?
Detecting the generation of a star. Oh, that's a question beyond my comprehension. That's an astro. I don't know, basically. Like when you look into the sky, whether you know that you're witnessing the birth of a star or not. That's a question, no? From Gautam? Isn't it a question?
Yes, sir, I think so.
From my capacity, I don't know the answer basically right now. Maybe I can answer, or we can Google it and find out. I don't know the answer for that. How we actually identify the actual moment in space.
Sreejith, just one point. I can just give a small intro to that answer. It may not be the full answer.
Yes,
actually, we do have very advanced telescopes in various regions, both optical, X-rays, etc.
Yes,
and unlike what we see, when you look at the sky, a very, very small area in the sky itself, the sky, the portion of a sky which is the size of a one rupee coin, that itself has got billions of stars. And with advanced space telescope, we can actually observe them. And then by seeing the kind of signals coming from the star, what I mean by the type of signals coming from the star is the kind of wavelength of the light which is coming from the star, we can say at which state of this cycle the star is. As you yourselves has pointed out, now when you have the process of the star being born and the star starts converting this hydrogen into helium, that is what you call the nuclear fission, significant amount of optical light, there is visible light comes out of it. So based on that only we say that at what stages of life the star is. So we basically say that when a star is born, when the star starts getting into the fusion process, because as you know now, initially everything is a dust of cloud, or a cloud of dust rather, that is what you call nebula. When they start coming to each other with gravity, then finally they start fusion. The moment they start fusion, they start developing energy, and that in that fashion you get huge amount of optical light liberating. And by properly studying and calibrating, we know that a star is being born. So that's what we do. The same thing is true in the reverse direction when a star is dying. When nothing comes out of something, we call it as a black hole. We say that there is a death of a star. So it's purely by observation.
Yeah.
Okay, thank you, Sreejith sir and Sreejith sir. So moving on to the next question is from Adil Prajesh. And the question is there any type of acids or alkalis or alcohol found in the sun?
No. Okay, that's a very interesting question. Type of acids or alcohols was the question, no?
Yes, sir.
You should understand that the chemical reactions happens with an element. When an element reacts with another element, an atom reacting with another atom to form a bond or something. All these things are related to the what we call the action of electrons. Okay, that's the nature, the number, and of electrons only defining its chemical characteristics, if you know. So all these things happen. Particularly if you look at the way life was formed in Earth, as per the Earth conditions, these atoms, the type of reactions that formed the alcohols or the acids and everything was very specific. If you see, I'm telling about the organic acids and all. So anyway, these kind of things happen as a response to the environment existing on Earth to some extent. Like this is happening on Earth because of the condition, the type of pressure, temperature, and everything exists. Simply, if you put it with the high temperature inside a nuclear reactor, if you can find an acid, you cannot find an acid. Normally, the normal definitions of acid stands. So, in the same way, the sun is nothing but a big nuclear reactor. The temperatures are so high, so normally you will not find signals. Not normally, it's not possible with the earth-turn chemistry that we discussed and studied so far. Yes.
Right, sir. So I think that was the answer to that question. And he's got one more question, which is there any chance that we may be able to travel at the same speed to light or near to the speed of light in the future?
Oh, that's an entirely realm of things. There's an impossibility with respect to the speed of the light. No, particularly accelerating, we cannot reach that speed. That's what I know. It may not be possible as a human being to speed up to the speed of light and be alive, and as a human being to travel at the speed of light. It may not be possible. Maybe Sreejith sir can add on to that.
Yeah, actually, theoretically, as said by the general theory of relativity, you cannot attain or cross the speed of light. But theoretically, you can reach very close to the speed of light, say 0.9%, 0.9, 90%, 99%. It's theoretically possible, but practically there is no means by which we can do that at present. With the best forms of, propelling ourselves, the accelerating ourselves by the rockets, etc. The technology is not good enough. Theoretically, you can say that you can keep on accelerating for years, and finally you will accelerate and finally reach the velocities one. But for that, the amount of fuels, etc., what you had to use is enormous. So right now, we don't have a technology to accelerate to that level. But of course, it's not ruling out that we will not have it tomorrow. Definitely, new forms of technologies may come out, new forms of developing energy may come out. It should be possible one day, hopefully, but today it's not possible.
Yes.
Right.
Okay, thank you, sir. And the next question is from Shreya. The question is that hydrogen and helium are less denser. So can you explain this with respect to the periodic table in comparison with the other elements?
That's so simple. What gives weight to an element is its neutron, okay, and proton. If you look at mostly these are having almost same weight, but neutron is having slightly higher because of the way that quarks fit into that. Anyway, the point is that because it is in the nucleus, it is having only, in the case of hydrogen, it is having only one proton. And in the case of helium, we are having only 4 numbers, that is 2 protons and 2 neutrons to be exact. So because this is less in number compared to the other elements, these elements, or in their gaseous form as molecules, are having low weight. Otherwise. Yeah.
Okay,
Yeah, Sreejith, they can also say with respect to periodic table, she was asking about why in periodic table it is coming in the first or second also, right?
Oh yeah, because the periodic table is arranged in the increasing order of their, nuclear masses, to be exact, atomic numbers or nuclear masses. So that's why we start with you arrange a number of people in your class in the order of their height in that way. So the shortest guy will be coming first in that sense. The similar way, the periodic table, the elements are arranged with the increasing order of their atomic weight, atomic number, whichever way. Yeah.
Okay, sir. So, yeah. Moving on to the next question. It's from Krishna Priya. The question is, can you explain the importance of iridium chemical and it's by what color?
Explain what?
Explain the importance of iridium chemical.
Iridium.
Yeah.
Iridium is having a lot of importance basically with respect to the, some electronics industry, some sensors. I don't remember right now, but it is having some applications. If you can Google it, you find out, but I'm not, I just written down something on iridium. For completing your answer, I'll just tell that. 1 minute. It is basically used, if you simply Google it, also you'll come. Because iridium, I'm not have much experience with iridium, but anyway, it is used basically, this is one basic important thing. It is used as a catalyst. What are catalysts? Catalysts are the materials which increase the speed of any reactions. So iridium is used in many chemical reactions as catalyst. And also for the industrial point of view as a product, it is also used in some spark plugs. And it is having much use in that way. Anyway, but it's a very rare element and it will be that way costly also. Yeah.
Okay, sir. I think she's got the answer. So moving on to next question, it's from Vaibhav. And the question is, what materials are used to protect a spacecraft from atomic oxygen?
That's a very important question. Who has asked that question?
Vaibhav, sir. Vaibhav.
Vaibhav, okay. This is a very hot topic right now, Vaibhav, because whenever we are, context, we need some materials to protect it from atomic oxygen, which is a highly reactive form of our normal oxygen. The type of material right now what we are using is a type of polymers called siloxanes. This is nothing but a long chain in which silicon and oxygen atoms are intermittently coming. Silicon, oxygen, silicon, oxygen, silicon, oxygen. The rest of the valencies of silicon is met by some methyl groups or alkyl groups. So basically, it's a long chain of siloxane. The advantage is that this particular polymer is, we can get it as a resin, like a paint you can apply on the metallic substrate, metallic anything on the, on the top of our satellites, and it will protect. How it will protect is simply, this siloxane is actually are reacting with the atomic oxygen to form a glass, silica, what we call silica, SiO2, that is getting formed on the surface. And that is actually protecting the further decay. So basically, the silica is a very good material for protection from atomic oxygen. But the way that we normally do right now is to coat the material with a siloxane polymer. Okay. Yes, sir.
I hope Vaibhav got his answer. And moving on to Adidev, he's asked 2 questions.
Yeah.
One of them being, how do space agencies prevent cold welding in docked spacecraft? And how is ISRO avoiding this in SpaceX?
Oh, that's I don't know the answer right now for that. But his question was about how do we do the cold welding?
In a docked spacecraft.
In a docked spacecraft. Oh, that I should get the answer from some metals, basically. I don't know the answer for that. Maybe I can get it. Sreejith sir, any idea?
Yeah, actually, you may be aware, no? This you're all aware about hot welding, normal welding operation.
Yes.
So in a normal welding operation, 2 metals are joined together by heat and pressure. Right? That's what we do when you see it on a workshop. But in space, what happens is if you have 2 materials with a very good surface finish, in the presence of vacuum, they join together. Okay, so this is what we call cold welding. This happens in any surface, any docked surface, any locking surface, even satellites, etc. So only method to prevent that welding is to provide some coating. And the best, one of the most common coating what people use is, in certain cases, we do anodizing. Okay, because anodizing is increasing the oxidation layer of materials like aluminum. But in many of the other applications, not just for docking, on differences, docking actually you don't really mind if there is a cold because once it's connected, it's connected. But it is actually used for some rotating surfaces like rotating solar panel mechanism, etc. So what people use is they use what we call the solid lubricants, right? So they will cover with a lubricant because in space you cannot use liquid lubricants because liquid lubricants will just evaporate and go. So they use solid lubricants like molybdenum and disulfide. They provide a coating on the surface. So when they provide a coating on the surface, that surface, when it rubs with another surface, it will prevent what this called this cold welding. Okay, so it's just to summarize, cold welding is provided by, we can say 1 or 2 methods. One is only provide enough surface finish as required. More surface finish means it will cold weld easily. Second thing is you provide special coatings like molybdenum sulfide lubricants. Third one is you provide anodizing. So these are the method universally applied irrespective of the application.
Oh, thank you, sir. Thank you.
Yeah.
Thank you, sir. So the next question by Adidev is, why do so many radioactive elements decay into lead?
Yeah, because, why, for answering that question, we should understand why lead is the last element of nuclear stability. You must have learned in your school classes also, a nucleus, when we can call a nucleus stable or not stable is a question. When there is the ratio between the neutrons and protons play a major role here. Whenever there is a higher number of neutrons to protons ratio is higher, the instability is caused by the fact that the neutrons always want to go out of the nucleus in that way. So that particular process in which that is happening is called the radioactive decay or something. So the reason for that is a big question. What defined? You will have some textbook answers for that, but still, for information, I'm telling the reason for that, the ratio being, how much important is the ratio for determining the stability of the nucleus is a big question. Anyway, for the time being, I can simply tell you that since for the elements beyond lead, that the neutron to proton ratio is higher, it is becoming unstable. Not all, of course. That's a question. That's not all the elements after that ratio is becoming unstable. Anyway, because of the neutron to proton ratio in the nucleus is in a very high or an unstable state only, that element will start to come to a very stable neutron to proton ratio. That's the process is what we call as decay. And the lead is the maximum in that. Number of neutrons is maximum is in lead. Beyond that, it will become unstable. That's why everything comes back to lead. Decay and comes back to lead.
Okay, sir. Thank you. And the next question is from Govind R. And the question is, why don't we make a nuclear engine instead of chemical engine in the rocket?
Yeah.
And is India trying to make nuclear engine in near future?
Okay. Who was asked that question?
Govind R.
Govind, it's a good question. What was the thought process in your mind? I was just thinking because all are chemicals, no? Because nuclear means this nuclear rockets were it's a new thing. It has started years back. If you see 1960s, 70s American popular science magazines, you will see that they have already started. They have started this particular program on nuclear propulsion, but at that point, because of the awareness with the people and understanding of the technology, the only thing what they know was it is used as a bomb. So people, the civil people, normal people were actually against that, and I don't know they have shelved it or not. But for any country, this kind of development is a highly secret business in the sense. But what I can tell from my understanding is that nuclear propulsion is a very promising propulsion in terms of its sustainability and easy of operation or something. But I cannot clearly tell whether India is actually having a program on nuclear propulsion or not right now. Yeah.
Okay, sir. So next question is from Shankar of class 8, and he's got 2 questions.
Yeah.
So how does boiling reaction change in microgravity?
Oh, that's very interesting question. Gravity, basically the boiling, if you see, boiling is happening when particularly in Earth's surface, when boiling happens, the vapor pressure, every material is having its own vapor pressure, having its own vaporized atoms on its immediate surface. So when that pressure generated by the vapor phase is equivalent to the atmospheric pressure existing there, that material or that liquid will boil. But this kind of situation is entirely different in space. If you in space, the question can be in different ways. One is under vacuum or under normal pressure. So okay, basically the boiling point is determined basically by the pressure on top of the liquid. If you see, because if you get enough the more type molecules on the liquid surface, if it is getting enough energy and the vibrations are good enough, because when we increase the energy input into a material, the vibrations increases and it comes to a point where it comes and stabilizes in the vapor stage. At that particular point, only thing matters is the vapor pressure basically, and so it depends upon basically pressure. The effect of gravity is entirely a different thing. I don't think basically that we have to see, but gravity is mostly from my survey understanding, but in literature what I've seen actually, to the best of knowledge, this gravity is actually playing a role in much another type of mechanisms where the materials, atoms are moving, that kind of a thing. But boiling will have an effect when you have vacuum on top of that. The boiling temperatures will be lower. It will boil at a lower temperature when the pressure is lower. In that aspect, in space, the effect of low vacuum will be there. But the gravity, we have to see. Right now I don't feel, or else I have to.
I'll just add one minor point apart from what you just mentioned. The process of boiling, like exactly like Dr. Sreejith has mentioned, that's the way it works. But gravity has got a role in heat transfer. Okay,
nice.
So in space, when there is a free, there is a different types of convection. So in Earth, what happens? When something gets hot, air gets hot, it just goes up. Okay, so that is what we call the free convection. So there is a particular term, what you call Grashof number, etc. which basically dictates, how much this free convection takes place.
Okay.
But whereas I think, as he has shown in the case of fire in space, the fire, the flame don't have a elongated tail. The tail will be spherical. So in space also, since there is no free convection, just because of a temperature difference, the fluid will not go around and mix. Okay. So the process of heat transfer within the fluid before the so-called boiling will have an impact. So accordingly, the boiling process itself may appear different.
Yes.
But the mechanism or the temperature at which this may happen is a different matter altogether. So it does have an impact, but not the way, in terms of suddenly changing from one state to the other. But the process of getting into that temperature will have a difference.
Process of heat transfer happening before the boiling will be different.
Exactly.
That's
Exactly. Yeah.
Okay, sir. Thank you so much. And so moving on to next question by Shankar. Can any reaction involving electricity, like electrolysis, see change while being in microgravity?
Can you repeat the question, Devananda? I couldn't get it.
Yes, sir. Can any reactions involving electricity, like electrolysis, see change while being in microgravity?
Electrolysis, whether electrolysis will have a difference in the microgravity environment?
Any reaction involving electricity, like electrolysis, I think he refers to as an example.
Yes. Basically, this are all coming in the same line of thing right now, because everything relates to the movement of this charge. Because the way that electricity moves varies in a conductor and an electrolysis setup where it moves as ions or something. So when it is moved in the conductor, when you are having a hot wire or something through which electricity is passing, it is through the energy levels of the electrons, or we call the electrons are flowing or something like that. But when it comes to a liquid, where an electrolyte, what we call, there are ions which carry the other part of electricity through that particular electrolytic container. So in that, if you see, the basic thing is the movement of charges. The movement of charges is happening by simple mechanisms through the that difference in the gradient of the concentration of these charges, basically. And since this involves the movement of molecules or ions, which is having actually an impact impacted by the gravity, as per the discussion that we are having right now, the electrolysis also will have an impact when the gravity is not there. Yes.
Okay, sir. So before winding up, just out of curiosity, I'd like to ask a few questions.
Yeah.
So one of them is, how do isotopes found in space, like in meteorites, provide clues about the early solar system?
Oh, that's about the evolution of how the solar system is formed.
Yes.
Sreejith sir, can you add light onto this?
Yeah, I think in a general way, Dr. Sreejith has already answered this question. Actually, it's not the solar system. It's even about the Earth, how it has formed. It's not just in a chemical level, but more like in an elemental level, but more like in compound levels. Okay, see, the solar system and the Earth's evolution, etc., have been mapped by different events. For example, the percentage of carbon dioxide in the atmosphere is an index of a particular time. For example, we know that at a particular point of time in the evolution of Earth, the percentage of carbon dioxide was different, etc., etc. And how we found it out, etc., we dig deep into the ice shelves. We take the captured, air, analyze the percentage of carbon dioxide composition, etc., etc. And then we say that this happens over a particular period of time. Similarly, if you take the coral reefs, etc., depending upon the seasons, only the coral reefs form different types of layers. So then we can find out, what is the kind of temperature, climate change, and all those things which has happened over a period of years. In fact, even people have found out, the day in an hour, the number of hours in a day, it was different certain millions of years ago, as from these kind of things. Okay, and from the other thing, that isotopes decay and all, you very well know there is a well-established process of carbon dating by which we say that, certain things are certain years of age. So this is how generally we use isotopes in a general sense, because isotopes are like ticking clocks. So right now, if you know that the amount of because a living thing will stop absorbing a particular isotope of carbon like C14 the moment it dies. So from that point onwards, it will be starting decay. So from the decay pattern, we will know that when these things have been living. So this is the way in which the typical isotope-based datings have been done, and that is the way it is used for generally finding out the age of something.
Yes.
Okay, so the universe things are find out, the age, etc. Find out, by the well-known method of what we call the red shift, blue shift, etc.
Yes.
From that, we find it out how far these things are moving away from, etc., etc. So that's the way it is. And the spectroscopy part already Dr. Sreejith has explained. Okay, so when you see that from a particular star, a particular frequency of light is coming, you know that a certain element is there. And if it shifts over a period of time, then we know that it is drifting away from the Earth. So this is the methods what we use.
Okay, sir. And so the next question, like in your point of view, if we were to develop a specific space periodic table with only elements from space, how would it differ from the one that we are using on Earth right now, like considering the extreme conditions in space?
No, actually, that's so coming back to the last slide I'm telling, apart from the, human-made elements that we have made using our nuclear reactors and particle accelerators, all others, what we got is from the cosmic dust, basically from the cosmic dust, which is always available as the raw material for making almost all the celestial bodies. So the composition point of view, will not find any, any difference in the sense that the periodic table, if you extend to the space, you will normally not find any difference except for the human-made elements that we have made. So that's the same thing. But the composition point of view, if you see which is abundant and which is less, that will be a different story. But it will it will follow the same periodic table for the universe also. Even if you are shifting to a new moon or Mars also, the same periodic table. The point is that this elemental periodic table is made by us for our better understanding based on the scientific experiments and understanding of data. So it is a human-made thing. So wherever we go, we take this reference with us for seeking out. If we find an entirely different kind of spectrum, for example, at one day from a star or from a celestial body that is never being seen, what I'm telling you is a spectral signature. Then at that moment we can think about a higher, artificial kind of material what we have produced. It is already produced in some star or something. But for reference purpose, our periodic table is well good for the whole universe for the time being.
Right, sir.
Yes.
So that is it for today's Q&A session. And thank you so much for sitting here with us. And yes, sir, thank you for today.
Okay, thank you.
Yes, sir. So for today's vote of thanks, I invite Albin.
So before that, I'll just put on word. Maybe can I?
Yes, sir. Sure.
Okay. Basically, at the end of this day, I just want to add on 2 more points. Thing is that I was just thinking about not about the questions. The questions sometimes can come in my area of expertise. Sometimes it cannot come in my area of expertise. I'm not worried about that. I was looking into the way that people are coining the questions. That is quite interesting and so quite reaffirming. So I congratulate the students for the questions basically. Of course, this space part is actually, I also study little bit, I read some books, but that is not my core part. That's why I was not able to answer some of your questions. But of course, Sreejith sir, the expert, was there. I also thank him for being for the this long duration. He was there always, and he's there as mentor and a person with a lot of ideas and guiding in such kind of things. So I personally put my thanks to the students, to the organizers, and also personally to Sreejith sir also for being with me throughout this lecture. Yeah, please continue.
So Albin, please continue.
Okay. Okay, sir. Good evening, everyone. I am Albin with Thomas. I am a BTech student. Okay, it's my privilege to deliver the vote of thanks on behalf of the UL Space Club for this today's inspiring webinar, Chemistry and Space, the Story of Elements. This session holds specific significance in that mark the 75th webinar organized by the UL Space Club, a remarkable achievement that reflects our dedication to spread knowledge and curiosity about the space and science. First and foremost, I extend my heartfelt gratitude to our esteemed speaker, Dr. Sreejith KJ, head of the Ceramic Matrix Composites section at Vikram Sarabhai Space Center, ISRO. Your valuable insights into the connection between chemistry and space have provided us with a fantastic, fascinating perception on the role of elements in the space exploration. Thank you, sir, for sharing your expertise with us today. I also thankful to the distinguished personality, Sreejith sir, present here. Your support and encouragement means a lot of us and motivate us to contribute hosting such meaningful events. I extend my heartfelt gratitude to Sri Sajil UK sir for expertly moderating today's session, enhancing a soft, smooth and encouraging experience for everyone present. Last but not last, a big thank you all the participants. Your active involvement and enthusiasm make this webinar meaningful. We hope today's session has been an educational and inspiring to everyone. Thank you.
Thank you, sir. Thank you very much. Thank you all.
Thank you, sir.